Definition 5.19. Let x dx and y dy be metric spaces. A bijective function f from x to y is called an isometry if the distance in x between points x and x prime is equal to the distance in y between the images of those 2 points for every pair of points x and x prime and x. If f from x to y is an isometry, then we say that the metric spaces x and y are isometric. So for metric spaces, an isometry is sort of a strong version of a homeomorphism. As we're about to show in exercise 5.31, if we have an isometry between metric spaces, then it is a homeomorphism. Okay? But it doesn't just preserve sort of neighborhoods like a homeomorphism does. It preserves distance, and therefore it preserves open balls. Okay? So it doesn't just map an open ball in X to some open set in Y, but it actually maps it to another open ball of the same radius. So let's give this exercise a try. We're assuming F's an isometry. We want to prove it's a homeomorphism. Homeomorphism is just a bijection for which F and F inverse are both continuous. So the first part's easy, since F is an isometry. It is by definition a bijection. So it remains to show that F and F inverse are continuous. Okay, well, let's show that F is continuous. Given any x in X, and alright, we're supposed to take any basis element of its image over here in Y, so any basis element be respect to the metric d sub y of f of x, a radius some epsilon, any such base element for y. Okay, and we have to find a neighborhood of x back here that's going to map into this epsilon neighborhood of f of x. And because distance is preserved, we can just take the open ball of radius epsilon. Okay, so I claim that if we apply f to the ball respect to the x metric about x of the same radius epsilon, that's going to be a subset of this ball of radius epsilon about f of x in y. So let's just sort of double check that or explain why it is. So in our picture up here, if we have any x prime in this ball and we apply f to it, I need to show that we end up inside of this ball. Okay, so suppose that x prime is in the ball about x. Okay, well then what that means is that the distance in x from x to x prime is less than epsilon. Okay. But that distance is equal to the distance in y from f of x to f of x prime. Since f is an isometry, and since it's equal, it too has to be less than epsilon. That means that that f of x prime is in the ball with respect to the y metric about f of x of radius epsilon. Okay. As desired, we took an x prime in here, applied f to it, and showed that we ended up in this ball. Okay. So f is continuous. What about f prime? Well, it's basically analogous. The proof that f inverse from y to x is continuous is analogous. Well, once we need our sort of isometry statement to work from. and I need it to be about f inverse instead of f. So I just need to rewrite this in terms of sort of flip it around. You use y's instead of x's. So let's write y equals f of x and y prime equals f of x prime. And we can deduce that, well, this expression here becomes d sub y of y comma y prime. And that's got to be equal to the left side here. Okay, and the x, it turns out, is going to be f inverse of y, so d sub x of f inverse of y, lowercase y, and caps lock is the culprit. And then the x prime is going to be f inverse of y prime. Right? Okay, so once we have that, this is the statement that f inverse from y to x is preserves distance, right, as an isometry. And now we can write the analogous proof to what we have up here, just sort of switching x's with x's with y's, x primes with y primes, and f's with f inverses. And that does it. We've shown that f's an isometry, we've shown that it's a bijection, and that f and f inverse are both continuous.